Welcome to e-Podasala lecture series in computer science. So we are going to discuss today about the combinatorial optimization problems. We are going to discuss about how to apply the brute force technique for combinatorial optimization problems. In particular, we are going to talk about 4 problems today. They are 15 puzzle game, 8 queens problem, knapsack problem, and assignment problem. In module 7, we discussed about the brute force technique. You can recollect that brute force technique is a straightforward approach based on the problem statement and the definition of the concepts involved. I was telling you that there is no specific strategy in brute force technique. We simply go through the problem statement and the definitions, and we are going to apply some sort of strategies to find all solutions in a brutal manner. I was also telling you some of the advantages and weaknesses of this kind of approach. The strength I can recollect or the wide applicability, in the sense that brute force technique is not limited to certain domains. We can apply to almost all sorts of problems in different domains, simplicity involved, and also we can get some reasonably good algorithms for some important problems. Also, we can use the design as a comparison framework. We can use the algorithms that are designed using the brute force technique as a benchmark for comparison purposes. There are certain weaknesses. We discussed about all the things in module 7. I just want to recollect some of those details. Some of the weaknesses are it rarely gives efficient algorithms, and also it is not very constructive or creative as some other design techniques. So today we are going to apply the brute force technique for certain combinatorial problems. What is a combinatorial problem? Combinatorial problems are those problems that use combinatorial structures. What are combinatorial structures? Combinatorial structures are sets, trees, graphs, permutations, and the Catalan families. In other words, we are trying to generate some sort of combinatorial structures. That means we are going to enumerate these structures and we are planning to solve the given problems. Combinatorial problems may also be a combinatorial optimization problem. What is a optimization problems? As the name suggests, these problems require optimal solutions. The structure of an optimal problem is like this. We should have some sort of an objective function. The objective of an application may be a profit, work minimization, or it can be a time factor. So combinatorial optimization problems do have an objective function, and we should have some sort of a feasibility criteria so that the solutions can satisfy these sort of things. Then you have a solution space. Solution space involves all possible solutions. These solutions are called feasible solutions. These are also called as candidate solutions, and you have some sort of an extremum requirement. Extremum is often maximization or minimizations. So the feasible solution that satisfies this sort of extremum requirement is called an optimal solutions. In other words, a problem can have multiple solutions called feasible solutions, and the solution that satisfies the extremum requirement and at the same time satisfying the feasibility criteria and at the same time maximize or minimize the given objective function is what we are calling as the optimal solutions. This is the general framework of obtaining the optimal solutions. So, given a problem, we just look to generate all possible combinatorial structures that represent all feasible solutions. In other words, we are going to list out all the candidate solutions of the given problem. And once the solutions are generated, then we are going to search for the best solution among the generated feasible solutions with respect to the feasibility criteria, extremum requirement and the given objective functions. This is the kind of general framework we have. When we apply this sort of brutal approach for combinatorial problems by generating all solutions, it often leads to some sort of an exhaustive search. Exhaustive search is nothing but a brute force technique that is normally used for solving the combinatorial optimization problems. So, in exhaustive search, as specified in the general framework, we are going to generate all possible solutions of the given problem. Then the solutions are generally available as a state space tree, a tree where all solutions are represented as a node, so that the given problem is transformed to a sort of search problems where we are going to search the state space tree for the optimal solutions. So, the least cost or optimal solutions are the solutions that we are looking for the given problems. The problem strategy seems so simple, but unfortunately applying this in practical sense is very difficult task. Why is it so? Because combinatorial problems are often very difficult and we encounter the problem called combinatorial explosion of structures. In other words, theoretically the solution is very simple, but practically it can't be applied. I can give you a small example. Let us assume that we are going to design a program for testing a binary bit. Let us imagine that the problem task is to test a criteria that involves the binary bit. Suppose if the bit is a single bit, then I require two inputs to test the program. In other words, the inputs are 0 and 1. If the bit size is increased to 2, then the number of inputs that I require becomes 2 power 2 4, that is 0 0 0 1 1 0 and 1 1. If the bits are increased to 3, suddenly it becomes 2 power 3, that is 8 inputs I require to test the given program. In other words, combinatorial explosion is a scenario where a small increase in the input leads to a large increase in the generation of structures. You can observe here in this particular table where the unit rise in the input leads to a large explosion in the output. Suppose if the number of bits becomes 1000, then 2 power 1000 inputs needs to be processed. As n tends to go towards infinity, the number of outputs becomes extremely larger and finding solutions becomes very difficult. This sort of scenario is what we are calling as the combinatorial explosion that often makes the problem difficult to solve. These problems are called the exponential problems. To give you a flavor of these problems, today we are going to discuss 4 problems. So, as an example, first we will take a problem called 15 puzzle game. Probably you might have played this particular game. So, here you are given a initial configurations and you have a target configuration, and the objective of this particular problem is to change the initial configuration to the target configurations using the operators top, bottom, up and down. In other words, if there is a possibility to move in the sideways or up or down using the empty slot, we can do that. So, as suggested earlier, this problem requires the generation of the state space tree, and we have to search for the target configuration that is present in the tree. If we generate the tree, it looks like this. The root is the initial configuration, and if I move the using the empty slot, a tile in these directions leads to the children, and the repeated application of these operators leads to a gigantic tree structure called the search space tree. So, here these are the terminologies that are involved. A root is the initial configurations. So, you can see all configurations will be present in the solution space tree, and once a tree is available, then I can search for the target configuration using a search technique like depth first search or the breadth first search. How to search for a particular node? For example, let us assume that A is the initial configuration, and let us assume that J and N represents the target configurations. So, if this is the case, so my game is simply reduced to a search problem where I have to search for my targets J as well as N. In other words, I have to see what is the path from the root to my target. So, this kind of search is what we are calling as the tree search, specifically depth first search. So, you can see very well I have to explore this in a systematic manner. So, I require some sort of an order. So, that is the reason why I go for the DFS. In DFS, what I will try to do is I will start from the node and I will just go to the depth searching for all the nodes, and once I reach a dead end, then if I do not have provision to go forward, then I will backtrack and then I will search in the alternative manner. This kind of search is what we are calling as the DFS. So, I will start from A, then B, then D. I am encountering a dead end. So, that means I will backtrack to B. So, I will explore E, H, L, dead end. Again I will backtrack, I will visit M, then I will visit N, dead end. This I will backtrack to, already these are explored. So, I will come here I, then O, then dead end I will backtrack to I already explored, E already explored, B already explored, A already explored, then I will visit C, then F, dead end I will backtrack to C, then I will visit G as well as J. In other words, the flow is going to be something like this. This kind of search is what we are calling as the DFS search. Another popular search is called the breadth first search, where I will explore the nodes in the level by level manner. So, that means I will visit A level 0, then I will visit level 1 nodes, that is B and C, then level 2 nodes D, E, F, G, so on. So, in other words, you can see very well the order is going to be level by level. So, this is what my exploration is going to be. This kind of systematic search technique or the traversing technique can be exploited for various problems. So, coming back to our 15 puzzle game, we have seen that we have generated a search space tree. So, in the search space tree we can use this and we can design the algorithms. So, the DFS can be implemented using a stack. So, this is how the prototype of the algorithm is going to look like. I am going to put the root node in stack S, and while stack is not empty, I am going to remove the node from the stack, and I will just see whether the node is a goal node. If that is the case, then I am going to return success, otherwise I am going to put all the children of that particular node onto the stack. So, this process will go on till the stack is empty. When the stack is empty and the goal node is not encountered so far, then we will return the failure. The same algorithm can easily be modified for the breadth first search by changing the data structures. So, here we can change the stack to a queue, and the same algorithm you can see is retained, but only difference between this and your earlier program is instead of stack we are going to use queue. So, now coming back to the 15 puzzle game, just recollect, we have generated the search space tree where every node represents a configurations. So, this is how the modification of the algorithms. So, the input is going to be a tree with a root, that is the initial configuration, and the target configuration. So, initially I have not visited any nodes, so I will just make it as 0. Then I visit root, I will change the status to 1, and I will generate the children W for the root, and I will just repeat for all the children. So, I will just check whether the node is visited. If it is not visited and if it is not a goal node, then I am going to invoke the DFS, and DFS is going to be invoked, and this process is going to be repeated till either the goal node is obtained or the procedure results in a failure. This kind of algorithm is what you will design for the 15 puzzle game. Practically, it is difficult to implement because the complexity of this algorithm is very vast. So, that means the algorithm needs to explore 16 factorial configurations. In other words, it is approximately 20.9 multiplied by 10 power 12 different arrangements of the tiles, and even if the configuration check requires a second, so the algorithm takes a huge amount of time. This is the biggest difficulty in the combinatorial optimization problems. But this is a game, this has to be faster. So, naturally we want a faster algorithm, therefore, we will just look into the efficient way of developing all the things in the later on modules. As of now, we can conclude that this is what guaranteed by the brute force technique. Second problem is also a very popular problem called 8 queens problem. So, the problem is something like this, where you have a given chessboard of size 8 by 8. So, this is the queen. So, the question is can you place 8 queens such that no 2 queens are in the attacking positions. You know very well, in chess queen is the most powerful what you say coin. So, this is the scope of the queen. It can move horizontally, vertically, diagonally. So, you can see very well this is the scope. The question is, can we place 8 queens such that the queens are not in the attacking positions. So, you can see very well the process goes on like this. So, in first column I will place 1 queen, then I will search for a better place to place queen in the second row. So, you can see very well this is one possibility, this is another possibility, this is another possibility. So, like that I will just keep on doing that, and hopefully if it is not possible, then we will backtrack and then we will again start everything fresh. So, this is how things will go. So, informally the algorithm for this is going to be like this. So, in step 1 I am going to try all possible combinations, and in all combinations I will check whether the queens are in the attacking position or not. So, if so, it is a success, otherwise it is a failure. I will just go back and then I will change the queen such that the process will continue. This is the informal algorithms. This is the formal algorithm for 8 queens problem. You can see very well we are going to generate a configuration like this as a solution, and if the solution is correct, that means if the queens are not in the attacking positions, then we will print the solutions, otherwise we will simply go and explore the other possibilities. Again, you can see very well the complexity analysis is a difficult task, because the board has got 64 tiles, 8 queens needs to be placed. In other words, this requires the possible selection of 64 C8 choices. You can see that the number of choices that needs to be make is very huge. In other words, if the number of tiles or the queens increase, the number of choices becomes very difficult. This is also one of the most difficult combinatorial problems that we encounter in algorithm study. The third problem is called the knapsack problem. Again, it is a very popular problem actually, which has been encountered many times in algorithms, where we are given a sack of size k and you have n different items, and every item is associated with a weight as well as a profit. It is also called as a value. The objective of this problem is how to load a knapsack as many items as possible, so that the profit is going to be maximum. This is the mathematical formulations where we are going to maximize the profit according to these sort of things. This problem was introduced by Tobias Dancing in 1950s, and we have two types of knapsack problems. One is called the continuous knapsack problem and another is 0 bar 1 knapsack problem. In continuous knapsack problem, we can put the fraction of the item onto the knapsack, like powders, gold powders we can put into the knapsack in fractions. 0 bar 1 is a problem where the item has to be placed in whole and it can be put in partial. For example, transistors, etc. Either you put the entire transistor into that or not. So, in other words, the fractions of the items are not possible. So, let us take this sort of scenario. Let us say this is the knapsack whose capacity is 4G and 4 kilograms, and these are some smaller items, and every item has got certain profit. So, the question is fine, I have to fill this knapsack. So, which is the better combination, so that the knapsack capacity is fully utilized and I will get the maximum profit. So, the informally the algorithm is going to be like this. So, I have to generate all possible subsets of the n items. So, that means 2 power n subsets are possible for n items. In other words, in this combinatorial problem, we are going to use the set as a combinatorial structure. So, I am going to generate a binary string of length for all these subsets, and if the item can be put onto the knapsack, means the binary bit is going to be 1, otherwise it is going to be 0. In other words, I will just explore whether the item can be loaded onto the knapsack. Suppose if the item can be loaded onto the knapsack, then I will get the profit that is associated with that particular item. And finally, I will just check the profit, and this I will repeat for all 2 power n subsets, and I will find out which combinations will give me the maximum profit, and the combination that gives the maximum profit is what we are calling as the optimal solutions. In other words, let us say you have an almirah, if you have some n items, the question becomes something like what sort of items you can put into that, so that you can achieve some sort of a profit kind of things. If you assume that every item is associated with some sort of a profit or utility value. So, this is how the formal algorithm is going to look like. K is going to be your knapsack, and W and P are the weights and profits of n items. So, you can see very well global profit is going to be 0, choice is going to be 0, index is 1. So, here I am checking, I am generating all the structures, and if item is included, you can see very well the profit is added, otherwise it is 0. So, this process goes on till all the subsets are explored. At the end of the algorithms, I am going to check the profit, and that is generated. So, for 3 items, the possible solutions are 1, 2, so 3, 1, 2, 1, 3, 2, 3, 1, 2, 3, etc., etc. Again, the complexity analysis is going to be order of n to power n. Similarly, you have the assignment problem where you have to assign a job to the worker, and that involves some sort of a cost. For example, let us say there are 3 persons, 3 jobs, and let us say if the jobs 1 to 3 is allotted to these 3 persons, then I will get the profit of 3 plus 3 plus 2. Again, this problem involves generation of all possible assignments like this, and you can see very well out of all the things the maximum profit is 19, and that is associated with the assignments like 132 or 231. In other words, this is the informal algorithms, and this is what the formal algorithm, where all the assignments are carried out along with the cost, and finally the least cost solution is preferred. Again, you can see very well the complexity analysis of this algorithm says that there are n factorial permutations are possible. Therefore, the complexity of this algorithm is order of n factorial. So, you can see as n becomes very larger, things are becoming very difficult. We can conclude this session by saying like this: brute force technique guarantee the solution, but often the solutions are inefficient, and in algorithm we encounter combinatorial problems. Combinatorial problems are of many kinds. We just surveyed quickly 4 problems that are most encountered in algorithms, and we applied the brute force technique. Later on, in the later modules, we will compare the better solutions with this so that we can know how efficient they are. So, we will meet in the next module as part of this course. Thank you very much.